we go. Okay, now it's working. I don't know. All right, so quantum computing. Hopefully we won't have to restart software once we have a quantum computer. Everything will just work better. All right, so what is quantum computing? Some of you in the room know. Some of you in the room have been or are my student presently. And you have some idea, but in general, it's not a future technology anymore. So quantum technology has existed for a long time. We've been exploiting quantum mechanics for technological value for I don't even know how many years. If you've ever had an MRI, you've been in a machine that relies on the principles of quantum mechanics. Okay, so medical devices forever have been doing it since the 70s. There we go. Now, quantum computing, the ideas have been around for a long time, but only recently have we really been ramping up and building industry devices and really actually trying to make this a reality. So probably about the past, let's say it's 2024. So let's say 20 years, it's become more and more and more and more exciting. And it has progressed from being a purely theoretical effort into what is now an engineering effort as well. So what does this mean? Right? So like, what is quantum technology? Specifically, what I'm going to be talking about today, computing, due to the current computational landscape. So it has a lot of applications. And, I often don't like to talk specifically about what the applications themselves are or will be, because it's pretty much anything where scientific computation takes place. If you do scientific computation, you probably use numerical routines somewhere, right? Quantum computers are going to somehow make some of your life a little bit better. However, they can also make your life a little bit worse, right? So the advent of this technology means that, current crypto standards, or not current, our existing crypto standards will be broken. And so we are implementing new crypto standards to protect against quantum attacks. So if anyone's heard of Shor's algorithm, Shor made it so that people can steal your credit card information, right? But we'll also potentially have applications to optimization. And we're going to be able to do new things like be able to probe the physical world better. And what I mean by this is like a lot of times if you're working in a laboratory, you have a computer, you want to know what's going to happen with your physical system, right? What do? Well, you sit down on the computer, you run some numerics, you simulate the thing, and then you say, okay, this is probably what happens in reality. Quantum computers are going to be able to make that kind of thing better too, or faster, I should say. Faster and potentially better, or potentially better and not fat, any combination. So, and as I said already, it's having a huge impact on the world because not only are we going to have this new technology that we can do new things with, but we were already forced to adapt to the potential future or the likely future where this technology exists. And it's probably not too far off. So basically today, well, actually in QSEC, we have a few different research trajectories, right? We have quantum computing, metrology and sensing, comms. We also do some stuff with materials. Patrick talked about yesterday. And we, what do you call it? Also have some education work that we do, but today is going to be mostly computing, and comms often falls under computing as well, just because quantum communication is closely related, but I am no expert on that, so I will not be talking about that. All right, so quantum computing. There's a few different facets of this. It's basically, there's a whole software stack, right? You have everything down from the hardware level all the way to the application level. And I'm hiding the ball a lot. So in between hardware and software, there's compilers, right? Algorithms are the things that you're going to be building, like that's going to be running on the machine. You've got to compile that stuff too. And then eventually maybe you can use these algorithms for actual real world applications that you care about. We hope. And we know of some, but it's going to take a few years before we have a machine like this that can be made small enough that we can actually, implement these things in any sort of useful way. And this picture here, this is the typical way that presently we talk about quantum computers, right? These circuit diagrams. And this is basically effectively the logical layout of quantum stuff. I think that is also rapidly changing as the field matures. And we are now writing algorithms that are going to look a little bit more like what you're accustomed to seeing if you're a computer scientist or something like that. But we're not there yet. So here's a timeline, historical one of quantum computing. So basically back in 81, Richard Feynman proposed the idea that, hey, I think it was on the, yeah, there we go. Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. So the idea is nature is quantum mechanical. You want to simulate quantum mechanics. Well, that's a really hard thing to do. So you probably want to go and actually exploit quantum mechanics to simulate quantum mechanics. Because if you try to exploit classical mechanics to simulate quantum mechanics, well, quantum mechanics would have been a lot easier to understand at the outset, right? If you could simulate it classically, it wouldn't be so hard to understand. And so in 85, David Deutsch introduced one of the first quantum algorithms. And this is like not the most exciting quantum algorithm, but shortly thereafter, we learned that you can turn this into an exponential speedup. So Deutsch's algorithm gives you an exponential improvement over classical computing if you do have a quantum computer. In 94, this is when things got real, okay? In 94, Shor introduced Shor's algorithm. And that's when everyone really started caring. And when I say really started caring, that's when like a small number of people really started caring, right? Before that, it was kind of just a curiosity, but Shor broke, the crypto standards of the time. And so everyone was like, hey, wait, if we build these things, we really got to think about what they can do, because they can clearly do things that we didn't believe they were previously possible and are also relevant in the real world. In 98, there's two qubit quantum computer. That doesn't sound like much, right? But it's not nothing. And eventually in 2001, this is when, I said the past 20 years, this is when we've really been like doing all this, what do you call it? All this advancement that we've seen recently, right? Which is where, okay, we can now use Shor's algorithm on a 7-qubit quantum computer, right? That's getting to be a little bit bigger. It's very difficult to get qubits to play together. So doing 7 qubits back in 2001 is no small feat. And then you can see the timeline progressively increases. Over here, we've got 51 qubits. In 19, there was this landmark paper by Google where they demonstrated quantum supremacy. And quantum supremacy was at the time the holy grail, right? This was basically, we built a device that can solve a problem that no classical computer can solve, and we can prove it. And so they did. So that was back in 2019. IBM objected because of whatever, they have a rivalry, but it still happened and most people still accept that this is what it is. All right, so this is basically, something's wrong with the way this is displaying. There's supposed to be another oh, it's there. There's supposed to be a triangle here. I don't know if you can see it, it's very faint. This is where we were like 5 years ago, 6 years ago. This was, what do you call it? These are predictions from John Preskill, and they're fairly consistent with what we're seeing right now, right? So this isn't us today. This is kind of us today. Okay, and it's true. We have seen some fault tolerance demonstrated. Okay, not much, but we're basically seeing it. So Preskill's predictions were pretty accurate. And so we're we're seeing something around the order of 1,000 qubits, a little bit less, maybe we're over here some, but we're getting right about there. And then eventually, we're thinking this is the outlook for the future. Well, we don't know exactly how far out this goes, but if we assume that, Preskill's time tracks with number of qubits, maybe we'll get here sometime soon, next few years, right? And people are actively working on this, and they're working on it very hard. And we need error correction in order to do very useful quantum computing. Noisy things, which is what we're dealing with right now, are not necessarily going to give you back anything particularly helpful. So here's a picture I like to show, which is trying to set everyone's expectations for what can you anticipate out of the future of quantum computing? Because a lot of the hype is, oh, quantum computers are going to go, they're going to solve everything, everything's better, the whole world changes, right? But the truth is, what we've got is we've really got something more along the lines of the advent of GPU computing, right? It changed a lot. It allowed us to do a lot of things we couldn't previously do, but we don't do everything on a GPU. So why do I put this picture up here? Anyone have any idea? So what? It is complex, but there's a reason I have this picture on the screen.
Child labor laws.
Child labor laws. Yeah, we'll talk about those in a second. So this is a GPU. This is a CPU. Okay? GPU is like having an army of first graders who are really good at addition, but they cannot do what this guy does. Okay, this is a professor. He can do all of this math. These kids, they can do some simple stuff. Now, if you need to add a bunch of numbers together, having this army of children is going to go way faster than asking this guy to do it, right? But if you need to do something complex, he's going to do it way quicker than they are. So this is going to be the sort of thing that we see also with a quantum computer, right? Quantum computer is going to be about the same. You're going to have like a central processing unit, probably a lot like the one on this desktop, and it's going to talk to the quantum army, whatever that means, right? So this is the way like code currently works. This is your CPU code. It's for computing this function. This is just something I pulled off the internet because I didn't feel like writing my own code, right? I don't actually know what this code does or why we implement this function. Maybe it's a Fourier transform or something, I don't know. But the point is, on the left side, you have CPU, it's very straightforward code. On the right side, you still have your CPU code, but then it farms off some of the simpler tasks in a smart way to its army of first graders. And so once we have a quantum computer, what we're going to be doing is we're still going to have our CPU code, and then it's going to farm off replace GPU side code here with QPU side code, your quantum processing unit. Okay. So, question? So, what makes quantum computing tick? If you've heard anything or read anything, you're going to say it's going to be a qubit. What is a qubit? Well, unfortunately, the best way to think of it is just a point on a sphere. And this is the block sphere. And so if you think about a classical bit, well, you can either be a 0 or a 1, up or down. So on the sphere, that's just the top point or the bottom point. The qubit can inhabit every single other point on the surface of the sphere, other than these two. And so basically what that means is whereas you only had 2 possible states previously, you have an infinite number of states now, right? And so you might think that with that infinite number of states comes infinitely more power. Turns out you don't get infinitely more power, but yes, you can exploit that to get some more power, and sometimes exponentially. So how the quantum computers work? Well, classically, people have probably seen an OR gate before. Quantum computers first have to be reversible. So we convert our OR gate into what is a reversible OR gate. So we have input 1, input 2, and we're computing their XOR down here. Okay. And we keep this thing around. You should be able to see that if you keep this information around, you can undo this operation and get back to where you started. So quantum computers have to be reversible. So they're built on reversible computing at the outset. And then over here, I don't even know why this is the quantum version. Sorry, this is the classical version. These are equivalent. Okay. The quantum version is just, in this case, the reversible XOR gate. So what makes it tick? You probably heard about Schrodinger's cat. So this is actually the complication with quantum computing. not necessarily the benefit of quantum computing. So the complication is that whenever you measure something, it chooses a state, right? Here it's both alive and dead. This is where you get a lot of your computational power from, where things are in the same state, in multiple states at the same time. As soon as it chooses a state, well, that's where things can go wrong. So part of the trick with making a quantum computer tick is going to be doing this at the latest possible date or only at an intelligent time or something, right? You only want to look when you can get the information that you want out. And what is the information that you want? Well, there's another principle here known as superposition. Superposition is basically, you probably saw this experiment if you took some physics or in high school or whatever, you shine some light through a hole and then it hits a screen and you get this interference pattern over here, right? Interference is something that you can exploit, and note that if you peek over here, right, if this is where you measure, well, then you have this high amplitude of seeing the center. So if you were looking for the center and you peeked at the thing that came through on this side, you'd see what you want. So the state it can choose is this, but this one is infinitely more likely. If you just so happen to be looking for that, this would be a good way to find that, even though your thing would collapse to one of the particular points on that screen. And we can exploit that. So how does it work? Well, serial computing is a lot like trying a bunch of keys in a row if you don't know which key works to open a lock, right? You try one, you try the next one, you try the next one. Eventually you get lucky and you can open the lock. Parallel computing, like we would do on our GPU or CPUs these days, right? What do? Well, you have a bunch of keys and like however many copies of the same lock, and you just try them all at the same time. What makes quantum different? Well, in this case, we have a single lock, and we can try all of our keys in the one lock at the same time. But we only get to learn partially which one worked. So we get back less information, but we only need one lock. And so if we can figure out a way to combine our information, well, then we're cooking. For instance, here, suppose that half our keys worked, right? Well, here, you still have to try every key in parallel. Here, well, you have a 50% chance, like on your first shot, that you've opened the lock. All right, so I'm going to skip over entanglement in the interest of time. Here is a chart of a bunch of companies that are presently working on quantum computing. And you can see like, it's like everybody major, and this list is growing. This is a few years dated. So we've got AWS, Microsoft. There should be, well, somewhere on here, I'm looking for Google. Maybe whoever made this is anti-Google. Nope, here they are, Google. We've got IonQ, which is going to be out there somewhere too. D-Wave is basically defunct, not really, but they're sticking around. But their stock went and took a dive. And then you've got some application end users. So like even people like JP Morgan, BMW, like it runs the gamut, runs the stack. So what about here at Mason? So this is, again, not the newest picture. Our group has grown, but some of the major people are still, or most of the major people are still here, I guess. And we've got a number of people working in quantum computing. I think now, if this were an up-to-date graphic, we'd have like 13 or something. I don't recall. All right. So what kind of research do we do here at Mason? What is it that, is going on here? I work on quantum algorithms. So I work on quantum compiling, and we have a couple of people who do that as well. We have folks who work on quantum machine learning. Presently, some people do quantum simulations. And when I say quantum simulations, there's two different ways you can do this. I look at them in terms of algorithms at the theoretical level, but we have other folks actually implementing them on current hardware. Classical simulation algorithms, so another side of the coin. is that if you want to give me a quantum algorithm, the first thing I'm going to do is see if I can find a classical algorithm that'll compete with it. Because it is cheaper to do something classical than it is to do something quantum. We have some complexity theory here a bit. And when I say a bit, I don't think that anyone is really deep in the weeds there, but you know, I do asymptotic stuff, which is, and every now and then I'll say something about NP, whatever. We've got some post-quantum cryptography going on. And again, we have a number of people interested in using NISQ devices for various purposes. And so NISQ are these noisy devices that we have available to us presently. Oops. Okay, so I'm going to give you an example of some specific research topics. And I'm going to focus predominantly on, I guess, my own research, not because I think it's more important, but just because it's what I'm most familiar with. And you know, it'll set the stage for what other people work on as well. All right, so one kind of thing you could look at is quantum walk. So quantum walk is a quantum version of a classical random walk. And you can use this to do things like solve constraint satisfaction problems. So think in that case, optimization problems, right? You want to find the best answer in a set of answers to something that, you know, has certain constraints to it. And you can get an exponential improvement on those sorts of problems, right, using a quantum walk over a classical walk. So classical walk would be a Monte Carlo algorithm. This is the state of the art of what we actually do with things. And a quantum walk can actually just get us there faster. Okay. So specific examples of research topics. I think this got juxtaposed, but anyway, the idea here is there are other folks who are presently trying to use quantum computers to do simulations of quantum chemistry. Okay, so they'll take a quantum chemistry model. Maybe you want to discover a new drug. Maybe you want to create a new material. They'll take it, they'll exploit quantum mechanics, shove it through a computer, and get simulations of what the quantum system is going to do in the hopes that they'll come up with something better than the state of the art in terms of drug discovery or what have you. People are working on NISQ devices, right? They want to be able to mitigate the error that these devices experience. They want to try and exploit them and use them for actual, excuse me, for actual applications, for actual gain. And so you have a number of people doing that. All these devices kind of look like this thing here. Well, not all of them, but a lot of them kind of look like this thing here. And it's this weird dangly doodad. Patrick can tell you more about what the picture represents than I can. I've been taking on a number of lab tours and I never know what I'm looking at. There's qubits in there somewhere. Okay, so I'm going to skip this. Let's just talk about really quickly how a quantum computer works and how you can actually expect to get some advantage out of it, because this is something that, you know, often gets lost, I suppose, in the mix. So this is going to be a lot like GPU computing. And I think that's the best analogy to go with. You don't typically get a quantum advantage or something by just sitting down and saying, I want to write a quantum algorithm for, I don't know, grocery shopping, right? I'm going to write quantum Amazon store. Like, that's probably not what you want to do. You probably have some problem. And what you do is you figure out a way to recast this problem as a problem that we already know a quantum computer can solve, right? So you take one problem and you convert it into one of these weird problems that we know a quantum computer is good at. Then we run that bit on the quantum computer, right? And we hope that that gives us a speed up. So that's where the power comes from, is you take one problem, you turn it into a different problem, and we already know that that problem is something that a quantum computer can handle, right? And so a lot of the magic is actually finding the problem, saying, oh, hey, this problem is going to work on a quantum computer, and then figuring out how to convert it into something a quantum computer is going to understand and be able to do something with in an efficient way. If you can't do the conversion efficiently, use the classical computer, right? Because you might spend more time trying to get the quantum computer to work than just solving the problem classically anyway. Okay, so preparation for research. A lot of you are young whippersnappers getting ready to get involved in stuff. So what do you really need to get started doing research in quantum computing or, quantum anything? Really, linear algebra, it's almost a must. And I say almost because I'm currently debating whether or not it actually is, and a strong STEM background. And that's about the end of it. You got those two things, you're pretty much ready to get started doing research in quantum. So yeah. There you go. So this is actually, I don't know why, so what are we doing right now? We have currently 2 dedicated quantum courses, and this number is growing. So there's going to be another one introduced in ECE pretty soon. We may have 3 courses. I think this slide was made before Jessica launched her. So we presently have 3 quantum computing courses, 2 in the physics department, 1 on quantum algorithms. There's going to be a course on post-quantum cryptography at some point, and there's going to be another course on the more engineering side of these quantum systems. So there's a lot you can take, and we also have this quantum computing seminar series. I highly recommend it. It's every Monday from 12:30 to 1:30. It's kind of late to advertise it for this semester. We only have 1 more meeting, but it does go every semester. It will probably be in the same location. All right, so what are people looking for in the job market? And I'm going to end on this slide because I'm basically out of time. People are looking for you to understand a lot of things. And really, if you're like saying, oh, maybe I'm thinking of a career in quantum at some point in the future, the thing that I guess we've heard the most is that people really want to see people who know enough about quantum to apply it to another domain that they care about. So like maybe you know something about quantum, right? You know how a quantum computer works. You know how to convert a problem into a problem that a quantum computer understands. But you have some domain expertise in something like systems biology or whatever, computational biology, right? Then you're a dangerous person in that market because you can make a real dent. And so, learning things beyond your own discipline can be useful. Learning things pretty much across STEM, any computational thing can be helpful in understanding quantum. And again, like there's a million different things that apply to quantum, are useful in quantum. It is becoming its own discipline in its own right, but it's still highly interdisciplinary, and it's still drawing a lot from a lot of different places. So you can really, come at it from a lot of different backgrounds. And so I think I'm going to end on this because there is not more. And I'm going to just say thanks because I'm officially at the end of my time slot.
Any questions? For those of you who are working with Cecil, this is a great chance to put him in the hot seat instead of you.
So anybody with vision working on quantum blocks?
I work on quantum locks.
Any questions? Comments? Complaints?
I have a complaint.
Good.
Not enough questions. Depth first search is what you're asking?
Yeah.
Yeah, so interestingly, Quantum Walk is able to do depth first search more efficiently than what would be classically possible. And that's what is kind of curious about this, right? Is that depth first search is deterministic, or at least it should be, right? And the Quantum Walk is not. Nonetheless, you can still do it because of certain properties of the Quantum Walk. The difference is you will get the answer with an expected runtime as opposed to a fixed runtime. But that's in the weeds.
think that it's probably not anytime in the future, but will the technology at some point be productive or towards just like the average person?
That's a hard question to answer. It's a hard question to answer because if people like me do my job right, or our jobs right, yes, but they won't know it. Right, like a lot of stuff right now happens on the cloud. All quantum computers, at least in the foreseeable future, are going to be housed by companies, and you're going to have time on the quantum computer, right? So you might be doing something, and company X, let's say Amazon, is like, oh, we got to fire this process off on the quantum computer. And so they'll go and fire the process off on the quantum computer, right? But you, the end user, won't know the difference. I think people who really will know the difference, will know what's going on under the hood, are going to be like the scientific computing community. I think that's really who it's going to impact, because if you look at who knows what's going on under the hood with like GPUs, for instance, right? It's really the scientific computing community, or the actual game programming community, I imagine. But it's not so much, what do you call it? Not so much the end user, right? The average person just has a GPU in their computer. It does what it's supposed to do because someone else wrote the software, and life is great. So at some point, the average person may end up with a QPU in their computer, and it does what it's supposed to do, but they won't know it.
To keep a discussion, like, what would you say is a common feature of problems with this problem?
A common feature. I mean, there's really only like a handful of quantum algorithms, and I hate being put on the spot with this because I always forget like half of the ones I'm supposed to know. But like historically, the quantum Fourier transform was like the thing, right? And we've found better ways, to do things than the quantum Fourier transform these days with things like quantum signal processing and whatever. But like once upon a time, the quantum Fourier transform just ruled all. And so it's just the fact that you could do this Fourier transform thing that, was able to do solve problems that were classically intractable. And then you just shoved everything through this and out popped magic, right? So I think that it's really a question of, is there a way to exploit interference such that somehow your circuit produces constructive interference on the solution you're looking for and destructive interference everywhere else? If I have to say there's a common feature, that's it. Interference is the most important property of a quantum computer that you don't get out of a classical computer. Right? Probabilities don't interfere. Quantum wave functions do. So it's the major distinguishing thing.
Okay, I think with that, we'll call it. Thank you, Michael, for an excellent talk.
Oh, I'll leave this up here.